Okay, we have attendance as well. Don't forget to do attendance 1202. It's a code. Okay, guys, let's get it started. Don't forget to do attendance. So we talk about pipeline. So you know how pipeline works. If you have a big task, we can break that down to small pieces and let multiple tasks start at the same time, but overlap these tasks with those small pieces. Okay, so that's called pipelining. If you have a big task, you can break that down to the pieces, and multiple tasks can run at the same time and overlap these small pieces. That's called pipelining. You can see that in manufacturing, in computer, in so many other jobs. So is pipeline always works good? Of course not, because sometimes those little tasks have some dependencies. You know, when you do two little tasks at the same time, sometimes those tasks have some dependencies that not let them to work fine. Can we fix them? Yes, it's possible to fix them. You're going to see some of them today, and some of them Friday, hopefully. So let's see. Why, first of all, why RISC-V is a good processor for pipelining. So any processor that can do these steps, fetch, decode, execute, memory, and write back regularly, I mean in the same clock, not in different ways, if they can run these steps, these 5 steps in one clock, that's a good design. Can we do that for RISC-V? I'm saying yes, because RISC-V is actually designed to be RISC, reduced instruction set architecture. So it means instructions are fixed. You remember when I talk regularity, when everything be fixed is easier for pipeline? You can see here the benefits of having like a similar instructions. Maybe you say, oh, maybe all computers are like that. No, it's not like that. Some computers, especially complex instruction set like Intel families, they have different size of instructions. They are not all 32 bits. Some of them are bigger, some of them are smaller, and that makes even fetching. Fetch is the simplest things in computer complicated. Even that step for those RISC computer become complicated. But for RISC is okay. For RISC-V, for this special architecture, for this special actually a computer is okay because they are all fixed, easy instruction. You can do fetch, and decoding is also easy because you don't have lots of instructions. You don't have that much big, for example, opcode. You have limited formats, and there is 2 input and 1 output that mostly is registered. So even decoding is so fast. What about execution? Execution can be done very fast too because it's just most of the time just registers. Register and registers very fast. You can do execution also very fast. What about memory? This is memory actually load store structure. So it means the only instructions that working with memory are load and store. So very limited. And also the creating the address can be done in a ILU part, in an execution part. That's also benefits. That helps too. You know, you are making this part one step before. So you're just going to access the memory. However, memory is slow, is out of the CPU or processor. So that's why most of the time when we want to choose a clock, we need to consider for pipeline, we consider the slowest one, that is actually memory. And write back is also in RISC-V is easy because they don't have multiple output, just one output. Can be memory or register, so it's just one output, can be done in one clock. So all of these steps in RISC-V can be done in one clock. So it's a great architecture for having pipeline. So how we can make the data path, that's a data path that we had before in RISC-V, or a simplified version of RISC-V in one cycle, but we want to make it pipeline data path. If you want to make it pipeline data path, how we can do that? You need to use multiple registers to store the values that you are creating in each step. Instruction fetch here, and then decode. So this is instruction fetch. Instruction fetch. So in instruction fetch, what we are doing, we are using program counter, check the memory, and also we can add increasing program counter also in this step as well. Instruction decode. In instruction decode, the resources that are busy this is important. You need to see in these steps which resources busy. Like memory here is busy. Register file here busy. This immediate is busy, but because we don't use it anywhere else, that's fine. And here ILU is busy, and memory again here busy. And then for write back, again register is busy. Register file is busy. Okay, so this is the resources that are busy. So what generally we are doing with putting some registers between states, we can make pipeline. So let's clean this up. So each stage work on a different instructions. That's very important. You know, when you are in this step, another instruction gonna fetch. So all of this stuff gonna go gone. You know, you need to save them in this register. And then the second instruction, decode, the third instruction need to get execute. You know, these values not valid anymore. It's gonna replace with the new information. That's why we need to use those huge, long registers. We call them pipeline registers. Implementing that in Verilog is also simple. We can see that in another work. Maybe we implement the structure that you did for one cycle. We can do it pipeline. It's not that complex. So these registers, we call them instruction fetch, instruction decode, because this register is between these two steps. So generally, we have 4 steps, 4 registers, 1, 2, 3, 4. Why we need this last one? Because we don't want to make accessing memory longer, because this is, if we don't use that, you need to add these 2 parts in one cycle. The cycle is going to be bigger than memory access. Anyway, I talked about that last class, so I'm not going to cover that. So, so what those registers doing? Those registers actually are storing intermediate values. That's what we are doing. Why? Because this value is going to run, gonna destroyed by another instruction. So we need to actually save them and store them to not destroy. Also, control signals. We need to also, I didn't mention control here. In the next slide, we're gonna see that as well. We need to also save control signals. Some control signals need to be done in a write back. So we need to pass them through these registers. That's also very important. As I mentioned, if you want to use a Verilog for that implementation, you just need to use, in Verilog, when you want to put that, synchronize with clock, you need to put pulse edge, for example. If you want to be rising edge, you also can put it in falling edge. We can see that later. But if you want to do this instruction in clock, instead of just equality, you need to do assignment. This assignment, this arrow, means it needs a clock for that. So it means how many clock we need to run this. If you put equal here, this can be done in just 1 clock. But if you put this assignment, it needs 3 clocks for running that. So this is what we want for implementing pipeline. Have you had that in before? Yeah, you had that assignment. Yeah, okay, perfect. So this is how we can use actually data paths, the pipeline data path, even in Verilog. Did I mention Python? Oh, okay. I'm just confused. I have headache now. Anyway, yes, Verilog. This is Verilog. It's not Python. Okay. So that's how we can have actually data path. What about control? As I mentioned, control is also something necessary that if we don't save them, is gonna overwritten in each step. Why we put control here and why not, for example, here? Any idea why we didn't put this control over there instead of putting here? Anything coming to your mind? Can I put control everywhere? Yes.
Yeah. So since it's in the first stage, it can decode the instruction as it comes in, and then it just passes it on as everything else moves with it.
Yes, but do we have any control signal in the first, in actually fetch decode part? No, we don't have any control signal. We can put this, make them in this stage. But we can do that actually. But the point is, most of the time, decoding is so fast. So we want to, because sometimes control makes some delay. So we don't want ILU sometimes is slower than at least that accessing to these registers, because registers are so fast. If we put some combinational logic there, it's not going to bother anybody. You know, it's not going to make the system slower. That's why we put it here. We also can put it here. Why? Because these signals, we don't use them anywhere. This signal is for write back, is coming from there. As you can see, for write back, we don't need to save them because this is one stage. It's like they are connected. They are in one stage. They are in one cycle, okay? So that's the reason. So we make control here, but we transfer them through registers step by step. Anywhere we use them, we use. If we not, we pass it to the other stage. So control signals from these registers going to there and there and then done. It's like making them and use them little by little anytime we want. Why we save them? Again, because another instructions in next step gonna be here and gonna decode and gonna make new control signals, and these control signals gonna overlap, overwrite in that one destroyed. So we need to save them and pass them through. Okay, so each stage uses only the control signals that needs. And for example, in execution part, in this step, we just need ILU control. In memory, we need memory read and write. In write back, we need register write as a control signals. Why this is work well? Because in RISC-V, why this is work well? I mean, why I put control here? Because the point is, instructions are all fixed and simple decoding, and actually consistent position for like instruction, source, destination. I mean, the decoding and accessing registers is so fast. That's why if you put control, no bother anybody. So it's fast enough if you put control in instruction decode. So that's important. You always put control in instruction decode. So same way as here. We can also put it here, but if you put it here, we need extra parts to put in these registers, makes them longer. Also, this is memory access, and you know memory is slow. We don't want to add more weight to that. So that's why we put it in decode, okay? Let's go for hazards. So as I mentioned, not always pipelining work great. Sometimes because in pipelining, we had same issue in that example of laundry room as well, you know. For example, in laundry room, folding and putting in a closet, somebody need to do that. These two are related. These two have some dependencies, and it's not easy to do that. How we can do that in computer? Well, there is so many ways to fix that. Like you can see dependencies here. Instruction, fetch need memory, decode need register, execute need ILU. This is the resources that we need. And memory need, again, data memory. But instruction memory and data memory are normally memory. They are memory. But if we want to, for example, in this instruction, we do the access if this is like load, for example, load instruction. You want to load memory, and here you need memory at the same time. In this instruction, you also access memory because instruction memory and data memory are memory. So this called having one resource at the same time called actually a structural hazard. That's the first hazard that we encounter most of the time, and is hard to fix. Most of the time with hardware we fix it. We duplicate the resources. If we want, for example, in this stage, if we, for example, that's why we have data memory and instruction memory in a different memory. You know, they are not same most of the time. So single memory has this problem. That's why we use data memory and instruction memory in a separate way. You know, we don't mix them together. We don't use just one memory for that. So this is a structural hazard because it needs like a structure to change. There is so many other ways to fix it. We can see that soon. But the best way is to duplicate resources. What about data hazard? Data hazard is it's obvious from the name. When the data is kind of is not created, but you use it in the next instruction. You know, an instruction using data before it is ready. So here you are adding 2 registers and putting X5, and this takes, for example, 5 clock to get ready, but you are in second clock needed in this subtract. You need that. You know, right? Imagine. Change the color. You use this instruction in this pipeline, and this is in this. Okay, here the value of X5 gonna written in this time. But when you need it, when you want to decode it, you need that. So you need X5 here, but it's not ready. If you use this, if you run this, the X5 is something else. It's not that real one that you did. So this is called data hazard. So this need to get fixed. How we can fix it? Any idea? Yeah. Any idea? Yes.
Could you add more instructions in between?
Yes, of course. But who's gonna do that?
Programmers or the
Compiler. Yes. Any other idea?
Add, like,
Delays. Yeah, we can do that's called a stall. We can put a stall. A stall means no operation. Don't put anything. No operation. Don't put just no operation. No operation is one of the operations in computer. You can put who? Compiler, not you. You are a programmer. You're not that. You don't know what's going on there. But compiler knows. Compiler knows how pipeline working. So it's try to fix the pipeline to not make hazards. Hazard is a problem for compiler, not for programmer. Programmer don't care about that. So the compiler need to fix that. Compiler can put some stall here, or some bubble, or some no operation, or as you mentioned, it can check to see which instructions doesn't need any dependencies and put them there. That's a great idea. So for example, these 2 instructions not related to these 2. So what about we run them here? Awesome. This is also possible. Okay, this is data hazard, but we have other hazards too that we call them control hazard. Control hazard happening when you have jump and branch. When this instruction is branch, and because the branch has some issue, and it need to actually you are checking the condition. The condition need to be true or not. So that's why sometimes condition is true, sometimes not. So the compiler cannot decide where I need to put this rest of the pipeline. If this is the jump instruction, we have 2 conditions. One is the condition is not true, so we need to go regular normally. And the second is when this condition is true, so we need to jump where somewhere fixed, like here. So all of this need to go to garbage. all of this information that already was inside the pipeline, and some of them even very ready to finish. We just need to flush it, put them out, and fill them with the new instructions, and everything gets slow and slow, even slower than before. Okay, that's called control hazard, happening when you have jump or branch or any kind of control instructions, changing control. Any question about hazards? So we have different type of hazards in digital logic. Remember, when we were working with gates and when we were working especially with memory, we had this kind of like situations that system makes wrong information. This is also same idea, but in terms of pipelining, this is happening too. Let's see what other ways we can deal with a structure hazard. As I mentioned, a structure hazard is happening when multiple instructions need the same hardware, same resource at the same time. So, for example, most of the time instruction fetch and memory, they are just, if we have just one memory, this is a structural hazard because we just have one memory and we want to write it, and at the same time we want to fetch, we want to access, and the memory just has one bus, doesn't have two buses, just have one bus, one address bus, one data bus, and you can't do two things at the same time. But in most of computers, specifically RISC-V, we can do that in actually because it's two memories, one for instruction, one for data. In this example, we can see when you do load a word, we access to memory with the address of x1, added with the index 0, and go to that address of the memory and load that in x5. So if you want, I don't know if I have the picture. Yes, I have a picture here. As I mentioned, this instruction even doesn't matter what is the next instruction. If you have a load, it means this part you are not bridging. You are using this part. As you can see, there is some bridge too, because some instruction doesn't need accessing memory. So, but this instruction is a load instruction, need memory, and when you go down, not in this, because they are okay, registers, memory okay, memory. These two are same source, and that's a structural hazard, a structural hazard. And to fix that, we need to, as I mentioned, you need to use different memories, one for instruction, one for data. Is any way to fix it? Yes, a stall. That's a normal way. A stall always works for any hazards. Anytime hazard happening, compiler can decide. Compiler can find it. Compiler, when try to compile the code, or assembler, maybe I'd say assembler, when try to change the assembly to the machine language, it's going to check, oh, here is a hazard. Maybe I put a couple of stall, couple of no operations here. But is that okay? No, because it's wasting cycles. Wasting, you don't want to waste processors, just don't do anything. So that's not a good idea to just use a stall. A stall is like that. You're just putting, and here you need two stalls, one here and one here. Actually, am I right? Oh no, actually three stall to instruction memory, for example, start here instead of here. And yeah, you can fill the stall, but it's lots of work to find some instructions that are not related, to keep them there, fit them there, to use in a proper way. Okay, that's a simple way to fix it. But there is other ways to fix it. First is to separate instruction and data that I mentioned. In instruction fetch, just use instruction memory. And in memory, you use data memory. That's good, no conflict anymore. Any other way? Yes, we can do another method. And actually, that's not another method, that's actually the same. We use enough sources. We use multiple. We use actually, for example, isn't it like oil you happening at the same time? No, but if happened, we can have multiple ILU, or register file also the same. Register file, it has another trick that I'm gonna tell you. Like for example, here, because register file and write back might happen, it's gonna happen at the same time. Instruction, yeah, here, look at this. In here, we use registers. And here, this register is in for write back, and this register is for decode. So that's also happening. Can we use two registers for this purpose? Any idea? Like what we did with memory? What about registers? Here we have registers for write back, and here we have register for actually decode. Any idea how we can fix this? Anything coming to your mind? Can we do two, like what we did with memory? No, why not? That's true, we can't. Why? Because you want to write it in the same place. If you have a two, how you can match these two together? How you can make this, align these two, because you can have two. You just have 32 registers, and you want to write back in the same register. Not two place for that. It has lots of problems. So no, you can't have two, but in a picture you can see something. You can see these different colors, and in instruction, oh no, yeah, here, as you can see here and here, they have different colors. Can you see that? So it means you can do write back. There is another trick. So because clock has some rising edge and some falling edge, what about we do rising edge for writing and falling edge for reading, for example? We can do that. Even in Verilog, we are able to do that. You can see that soon. So that's another way. Another way is to just put stall. And a stall is nothing, just no operation. And it's worst case scenario, it's like a fallback solution. Any question about this picture? Here is very small, but here you can see that this is for the timing. Oh, sorry, here. This register and register, the timing between this and this is different. There is something here showing this is for example, falling or rising. So that's called clock phases. Using clock phases to avoid register conflict. Clock phases, because you have, for clock, you can synchronize your secret with rising or falling. You can do like this. Okay, always do, for example, instruction decode in falling and instruction write back in rising. You know what I'm saying? In this case, when you are writing back, at the same time, you can also do decoding and read from that as well. But the rest are, for example, however, if you want to make the colors all regular, I mean, similar. So this is also done, for example, and this doesn't matter, you know. Okay, so that's called using clock phases. And that's a very good trick. Some computers following that, I think RISC-V doesn't have that as a normal way, but MIPS had that. That's why we still can change RISC-V to have this as well. So the idea is to, instead of adding extra hardware, we can split a clock cycle into two halves to safely share the same resources. This is possible for memory access as well. So first half you do, for example, one operation. The second half you do the second operation. And for example, write back and decode in write back, you can write to the register file. Happens in the first half, as you can see, writing happen in the first half. So you use this clock, rising. And for decode, you can use, because they are using same register file. We can have two register files, as I mentioned. In this case, for decode, this can happen in a second half. As you can see here, it becomes active with the rising edge of the clock, something like that. You can design the hardware to do that as well. Okay, and this is the way that you can have in Verilog rising edge, pose edge, and neg edge for falling edge. You can use that. You can use, for example, however, this code is for something else, but is not. But you can see how we can synchronize one thing, like assignment. This is still assignment, but you can do it with the rising edge or falling edge. This is possible in Verilog. Okay, and the rest is actually the last is a stall. So a stall, most of the time, as I mentioned, a stall can solve this any of these hazard. However, I'm going to talk about other hazard later. But in this example, I use one of these hazards. That is data hazard. So in this example, the compiler need to find dependencies. Finding dependencies is one issue. You know, you need to see which. As you can see here, you are adding these two. It is actually moving because it's x0 is trying to move x1 to x19. But this is going to get ready in a write back, but you want to use it in decode. In decode, you need x19. And decode to write back need two stall, at least. So you need to put two stall in this between two no operation here to can access this, because in this write back happening in the first part and this decode happening in the second part, so it's okay. With just two no operation here, you can fix this problem. This is data hazard. We're going to see that also more about that next class. So this is how compiler can use no operation or a stall. The stall or no operation is something that we need to, the compiler need to do that. It went too fast. Okay, so, and next class, we're going to talk about other hazards. Any questions? Did I talk too fast today? Okay, but I think we have some time. If you have any questions, let me know. Let's see what I can mention.